Hello and welcome to this video on how to specify a second-order growth curve model in the Mplus software. My name is Christian Geiser. On this channel I present weekly statistics tutorials, usually related to structural equation modeling or other multivariate statistical methods and often involving the Mplus software. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional resources, including a link to my weekly newsletter where you can get statistical tips and also to other videos and workshops. So in this video here, I want to show you the syntax for a second-order growth curve model in Mplus. Growth curve models are used to analyze longitudinal data, and oftentimes people use so-called first-order growth curve models where you have a single indicator at each time point. And there are certain advantages to using multiple indicators though, because with multiple indicators you can test, for example, the assumption of measurement equivalence across time, and also you have more power to detect inter-individual differences in change across time. And so one way to use multiple indicators in a growth curve model is by using a so-called second-order growth curve model, in which you have the growth factors as second-order factors. And that's what I want to show you here in this syntax. So here in this file, I have a longitudinal data file where we have 4 measurement occasions and 3 indicators or 3 observed variables at each time point. And so we want to model growth across these 4 time points. We're assuming they're equally spaced here for simplicity, and also we're assuming that we want to just simply model linear growth. So this syntax here is for a linear second-order growth curve model. And so the first thing that we do then in our model statement is we specify the first order factors, and oftentimes they are referred to as latent state factors in the context of latent state trait theory. For example, latent state trait theory is a measurement theory for longitudinal measurements, and so these are called state factors because they may contain state and or trait and state residual components, meaning they can have components that are due to the person, and they can have components that are due to situations and person by situation interactions. And now with our second order growth structure, we model that trait and trait change structure, whereas with the first order residuals, then those would be the state residuals in the sense of latent state trait theory, meaning those state residual factors, they reflect situation effects, and or person by situation interactions, meaning time-specific effects. If you're more interested in latent state trait theory, then check out other videos on my channel where I discuss latent state trait models in detail and how to specify them in Mplus. So this here is a first order model with latent state factors, and so therefore they're called tau, because that's how they're referred to in the context of latent state trait theory. Oftentimes tau for true scores, so to say, in analogy to what we would do in classical test theory. And so here those are the latent state true score factors for each time point. And you can see we have tau 1 for time 1 with the 3 indicators that are measured at time 1. So they have the same last index 1 for the first time point, and then they have different indices for the different indicators 1, 2, 3. We have the same indicators at time 2, and now they have the index 2 at the end for the second time point, and then here for the third time point they have the index 3 at the end, and so on. Notice that in these measurement models here we constrain the loadings to be time invariant. So that's the implication of measurement invariance or restriction of measurement invariance, where the loadings are set equal across time to ensure that the tau variables are measured in the same units of measurement across time. So we call that metric invariance or weak factorial invariance, when the factors have equal loadings over time. And so that ensures that their metric is comparable across time. Now that's not enough. We'll see later that we also do something with the intercepts to have not just weak or metric invariance, but also strong or scalar invariance as well. So this first of all sets up the measurement model for the first order factors with time invariant loadings for measurement equivalence across time. Next, we pick one reference indicator for which we set the intercept to 0 at each time point. And so this is here our first indicator. Why is it the first indicator? Why do we select the first indicator as reference? First of all, it is arbitrary which one you pick. It doesn't really matter, but Mplus by default sets the loading of the first indicator to 1 already. So basically Mplus by default chooses the first indicator as reference because it's kind of arbitrary in many situations, and so therefore Mplus uses this default setting, and so you have this loading fixed at 1 already, and then it makes sense if that indicator already has a fixed loading at 1 to also then set the intercept for that indicator to 0 at each time point, so that that indicator then has a fixed loading of 1 and an intercept of 0. What does that do? That helps identify not just the variance, but also the mean of the latent factor tau at each time point. So the first order factors then have an identified metric and an identified mean, and that allows us then to model the mean structure at the level of the growth factors. And so this makes the first indicator the reference indicator with a loading fixed to 1 by default and the intercept fixed to 0 at each time point as well. Now that has another consequence, and that consequence is that this indicator also has time invariant parameters because the loadings are equal to 1 at each time point and the intercepts are set to 0 at each time point. So that means this indicator has also measurement invariance, or for this indicator measurement invariance holds. Now there are other ways in which you could identify the mean structure. You don't have to go this way with fixing the intercepts to 0 for a reference variable, but it's one way to do that. The next commands here refer to the intercepts of the remaining non-reference indicators. So those non-reference indicators, they also have intercepts, and the intercepts are freely estimated. However, we want them to be constrained to be equal across time, because for strong or scalar measurement invariance, not just the loadings have to be time invariant, but also the intercepts. Why is it important to have strong or scalar invariance in a latent growth curve model? That's important because only scalar invariance makes the mean structure interpretable. So the mean structure, meaning the mean structure of the growth factors, because that ensures that the factors not only have the same units of measurement, but also the same origin of measurement, so that mean differences across time are meaningfully interpretable as differences due to change over time, due to latent change, so to say. And so therefore we give the label A2 for the intercept of the second indicator, and the label A3 for the intercept of the third indicator, so that for a given indicator also the intercepts are constrained to be time invariant. Next, we have a statement here that sets the intercepts of the latent first order factors to 0, and that's necessary because in a growth curve model the mean structure is fully explained by the second order growth factors. So there is a second order intercept factor that has the mean structure or represents the mean structure at time 1, and there's also a growth or slope factor that represents the mean growth rate. So the mean change comes from the slope factor and the initial mean comes from the intercept factor, and therefore we don't want those tau factors to have intercepts, because that would mean that there would be some other source of a mean structure, and that doesn't really make sense. It's the same thing when you have a first order growth model. You would also implicitly or explicitly set all the intercepts of the observed variables to 0 when the observed variables are directly used as indicators of your intercept and slope factors. Now here this is different, because here the observed variables are indicators of the first order state factors, and so they do have intercepts that are estimated, at least for 2 out of 3. We do estimate the intercepts here, because here the variables are not directly used to indicate the growth factors. But the indicators of the growth factors here, the tau factors, they have to have intercepts that are set to 0. Otherwise, the mean structure wouldn't be identified and wouldn't make sense. And then here, in this line of code, we specify our intercept and slope factors. And so in this case, I call the intercept factor Xi, again, to be in line with latent state trait theory, because in latent state trait theory, Xi indicates the trait. And so the intercept factor in a second order growth model can be interpreted as the trait score, so say, or the factor that represents the trait scores at time 1. So that's a person-specific factor that indicates true individual differences that are due to person effects only in the sense of latent state trait theory. So that's the trait at time 1, which is called Xi1. And then the next factor here, Xi21, is a trait change factor. So that's our linear slope or linear growth factor that represents linear changes over time, and it's defined to be the difference in trait factors between time 2 and time 1. And then the difference is the same given equal spacing over time. This factor, so say, has a constant change influence over time with the same rate because it's linear growth. And so this is how we set up the two factors. Here, the labels here, of course, are arbitrary. You could also call them intercept and slope, so to say. And then here we have our indicators of the second order growth factors, tau 1 with a loading of 0 on the slope factor, tau 2 with a loading of 1 on the slope factor, tau 3 with a loading of 2 on the slope factor, and tau 4 with a loading of 3 on this linear growth factor. So these at symbols here refer to the loadings of the first order factors on the slope factor. On the intercept factor, all the loadings are equal to 1 and fixed to 1 by default in Mplus. So you don't have to say anything about the loadings on the intercept factor, because in this default syntax for specifying a growth model, only the slope loadings have to be defined. The intercept loadings are 1 by default. The last comment here refers to the mean structure. So the mean structure of the latent factors tau comes from the intercept and slope factors, meaning from the trait, the initial trait factor, and the trait change factor. So those two are estimated, and we have to tell Mplus this so that those will not be set to 0 by default. So we're estimating the means of the intercept and slope factors Xi1 and Xi21, because this is, so say, where our growth, our mean growth is represented in this model. So the mean structure on the one hand is represented here by intercepts, which allow the indicators to differ in their means at a given time point, because they might have different means. But then also the mean structure is here in terms of the latent mean and latent change in the means that is represented by those growth factors. In another video, I will show you the output for a model like this. One thing that I still want to mention is that oftentimes a model that is set up like this won't fit very well, because when you have indicators that are not perfectly unidimensional across time, and when they might have indicator-specific effects, then you might find that the error terms of the same indicator across time are related. So you'll see that there's misfit, and then the modification indices or residuals might tell you, oh, there are residual associations between, for example, y11 and y12, because that's the same indicator across time, and so the error terms are correlated for that indicator. And so one way to address this that is common is to allow for correlated errors of the same indicator across time. I'm personally not a fan of this approach, and on this channel I present a different approach that can be applied to longitudinal data, where you have indicator-specific factors instead that represent the indicator-specific covariance across time. And so if you're interested in that, then check out my other video on how to avoid correlated errors in longitudinal data and how to model such effects with indicator-specific factors. If you like this video, then please hit the like button. Don't forget to subscribe to this channel and to check out the description for additional resources. You can also leave a comment in the comment section, and I'll see you next week.